Right now, somewhere above us, a telescope is floating in space. It is about 1,000,000 miles from Earth. It is cold out there, colder than anything you have ever felt. And in that frozen silence, this telescope is doing something no instrument has ever done before. It is not looking at stars. It is not looking at planets. It is looking at nothing. Or rather, it is looking at the space between things, the emptiness, the void, and what it found there has changed everything we thought we knew about the universe. The James Webb Space Telescope just helped scientists build the first real map of the invisible universe. And it is not a rough sketch. It is not a guess. It is a detailed portrait of the hidden material that holds everything, and I mean everything, together. Time, ones, the stars, the galaxies, the planets, you, me, the chair you are sitting in. All of it is being held in place by something we cannot see, something we cannot touch, something we have never directly detected. And yet, without it, none of this would exist. Not the Milky Way, not the sun, not the earth, not the ocean, not the air in your lungs. Scientists call it dark matter. And until very recently, we had no real picture of where it was. We knew it was out there. We knew it was heavy. We knew it pulled on things. But we had never mapped it. We had never drawn its shape. We had never seen the web it weaves across the cosmos. That just changed. In January of 2026, a team of researchers released the most detailed map of dark matter ever created. They used data from the James Webb Space Telescope. They measured the light from nearly 800,000 galaxies, and from that light, they traced the outline of something enormous, something invisible, something that stretches across billions of light years. A web, a scaffolding, a skeleton of the universe that was always there, hiding in plain sight, holding the cosmos together like the bones beneath your skin. This is the story of that map. This is the story of how we went from guessing to seeing, from hoping to knowing, from squinting in the dark to opening our eyes for the very first time. And it starts, as many of the best stories do, with a simple question. A question that has haunted scientists for almost 100 years. What is the universe really made of? Let that settle in for a moment. Think about it. You look up at the night sky. You see stars, thousands of them, if you are far enough from the city lights. Maybe you see the faint smear of the Milky Way cutting across the darkness. It looks full. It looks busy. It looks like a lot of stuff. But here is the truth. Everything you can see up there, every star, every galaxy, every nebula, every dust cloud, every planet, every moon, all of it, every single bright and beautiful thing your eyes can pick out, accounts for about 5% of the universe. 5%. That is it. The other 95%? You cannot see it. Nobody can. About 27% of the universe is made of dark matter, and about 68% is something even stranger called dark energy. We are going to focus on the dark matter tonight, the 27%, the invisible weight, the silent architect, because here is what makes this so remarkable. Galaxies in our universe seem to be achieving an impossible feat. They are rotating with such speed that the gravity generated by their observable matter could not possibly hold them together. They should have torn themselves apart long ago. And yet here they are, spinning, glowing, intact. Something invisible is holding them together. That something is dark matter. And it is not rare. It is not subtle. It is not marginal. It is the majority. It is the rule, not the exception. The visible universe, everything you can see and photograph, is the exception. We are the anomaly. The bright, noisy 5 minority in a cosmos dominated by the silent, invisible majority. And that realization changes everything. It changes how we think about ourselves. It changes how we think about our planet. It changes how we think about the night sky. Because every time you look up, you are seeing only the thinnest layer of what is actually there. Behind every star, between every galaxy, woven through every empty patch of darkness, the dark matter web stretches on, holding, connecting, building. Scientists call it the missing mass. But that name has always been a little misleading. It is not missing. It is right there, everywhere, all around you, streaming through your body at this very moment. Particles, or whatever dark matter turns out to be, passing through the earth, through the walls, through the air, through you, without stopping, without interacting, without leaving a trace. Trillions of them. Every second, and you feel nothing. But the universe feels everything. The galaxies feel the pull. The gas feels the pull. The cosmic web is shaped by the pull. And the 2026 map, for the first time, lets us see the shape of that pull in exquisite detail. There is a generation of young scientists growing up right now who will never know a world without the dark matter map. For them, the invisible universe will not be an abstraction. It will be a fact, a documented, measured, mapped, and published fact. They will study the web in their textbooks. They will see the blue contours of dark matter overlaid on galaxy images in their lectures. They will take it for granted, the way we take it for granted, that the Earth orbits the Sun. And they will build on it. They will make the next map, and the next, and the next, until someday the full atlas of the invisible universe is complete. That is the legacy of the 2026 discovery. Not just a map, a foundation, a starting point, a first chapter in a story that will take decades, maybe centuries to finish. The story of how we learned to see the invisible, how we mapped the dark, how we found the scaffolding of reality. We are living in the age of the invisible atlas, and it has only just begun. Dark matter does not glow. It does not reflect light. It does not absorb light. It does not block light. If you shine the most powerful flashlight in the universe directly at a clump of dark matter, the beam would pass right through it, as if nothing was there. You could walk through dark matter and never know it. In fact, right now, as you listen to this, dark matter is probably streaming through your body, through the floor beneath you, through the walls of your home. It is everywhere, and it touches nothing. It interacts with nothing except gravity. And that one interaction, that single connection to the rest of the universe, is enough to build everything. Think of it this way. Imagine you are standing on a beach. The wind is blowing. You cannot see the wind. You cannot grab it. You cannot hold it in your hands. But you can see what it does. You can see the sand rippling. You can see the waves rolling. You can see the palm trees bending. The wind is invisible, but its effects are everywhere. Dark matter is like that. We cannot see it, but we can see what it does. We can see galaxies spinning faster than they should. We can see clusters of galaxies holding together when they should be flying apart. We can see light bending around what appears to be empty space. The wind is blowing, and the trees are moving. That analogy has guided astronomers for decades. But the 2026 map took us to a completely new level. It did not just tell us the wind was blowing. It showed us the shape of the wind. It showed us where the gusts were strongest, where the calm pockets were, where the invisible currents flowed. For the first time, we have a weather map of the dark universe, and it is breathtaking. To understand why this map matters so much, let us go back in time. Way back, let us go back to the 1930s. Picture a man named Fritz Zwicky. He was a Swiss astronomer working in California. He had wild hair and a sharp tongue. Colleagues described him as brilliant but difficult. He did not care much about what other people thought. He cared about the math. And the math was telling him something strange. Zwicky was studying a massive group of galaxies called the Coma Cluster. This is a collection of over 1,000 galaxies, all bound together by gravity, orbiting each other in a slow cosmic dance. Zwicky measured how fast the galaxies in the Coma Cluster were moving, and then he calculated how much mass the cluster would need to keep those galaxies from flying off into space. The answer shocked him. The galaxies were moving too fast, way too fast. Based on the visible matter alone, the stars and gas and dust, the Coma Cluster did not have nearly enough gravity to hold itself together. The galaxies should have been flung outward long ago. It was like watching a merry-go-round spinning so fast that the riders should be thrown off. But somehow, they are still holding on. Something invisible was providing the extra grip. Zwicky called it Dunkelmaterie, dark matter, in German. And the science world mostly shrugged. It was 1933. People had other things on their minds, and Zwicky's personality did not help his cause. His idea was too strange, too bold, too outrageous. It sat on a shelf for decades. Then came Vera Rubin. It was the 1970s. Rubin was an American astronomer who faced a different kind of obstacle. Not just the mystery of the cosmos, but the fact that the scientific establishment was not always welcoming to women. She was once told that Princeton did not accept women into its astronomy program. She went elsewhere. She persisted, and she changed the world. Rubin and her colleague Kent Ford used a powerful new instrument, an image tube spectrograph, to measure the speeds of stars inside spiral galaxies. They started with Andromeda, our nearest large neighbor, and what they found was stunning. In our solar system, the planets closest to the Sun move fastest. Mercury zips around. Neptune plods. This makes sense. The Sun holds most of the mass, and the closer you are to it, the stronger the gravitational pull, the faster you need to move to stay in orbit. Everyone expected galaxies to work the same way. The center of a galaxy is brightest. That is where most of the visible mass is. Stars near the center should move fast. Stars near the edge should move slow. But Rubin found the opposite. The stars at the edge of Andromeda were moving just as fast as the stars near the center. The rotation curve was flat. It was like discovering that the outermost riders on a merry-go-round are somehow spinning at the same speed as those near the center. That should not happen, unless there is extra mass out there. Mass you cannot see. Mass that extends far beyond the visible edge of the galaxy. A halo of invisible matter, wrapping around the galaxy like a cocoon. Rubin studied galaxy after galaxy, 60 of them. The result was always the same. Flat rotation curves, every time. Something unseen was out there, something massive, something that surrounded every galaxy she looked at. Zwicky had been right all along. The universe was full of matter that nobody could see, and it was not a small amount. It was not a rounding error. It was the majority. For every spoonful of visible matter in the universe, there were about 5 spoonfuls of dark matter. We were living in a universe where most of the stuff was invisible, and we had only just noticed. But noticing is one thing. Understanding is another. The discovery of dark matter set off a race to find the particle. Because if dark matter exists, it must be made of something. Some kind of particle. Some new entry in the periodic table of the cosmos. For decades, the leading candidate was a type of particle called a WIMP, weakly interacting massive particle. The name told you everything. It was massive. It interacted weakly. And it was, in theory, just waiting to be caught. Scientists built enormous detectors deep underground. They filled tanks with liquid xenon. They waited in the dark, in mines, in tunnels, for a dark matter particle to bump into an ordinary atom. And they waited, and waited. Decades passed. Billions of dollars were spent. And as of right now, no one has caught a WIMP. Not one. The most sensitive detector in the world, called LZ, has been running for years. It has set record-breaking limits on what dark matter could be. But it has not found the particle itself. We are still searching. We are still in the dark about the dark. And that is exactly what makes the 2026 map so important. Because while particle physicists were digging underground, looking for the thing itself, astronomers took a completely different approach. They stopped trying to catch dark matter, and they started trying to map it. You do not need to hold the wind in your hands if you can draw a picture of where it blows. And that is precisely what the James Webb Space Telescope has done. It has drawn the picture, the first real atlas of the invisible universe. So how do you map something you cannot see? How do you draw a picture of what is invisible? The answer comes from one of the most beautiful ideas in all of physics, and it was first imagined over 100 years ago by a man with messy hair and a very big brain. Albert Einstein. In 1915, Einstein published his theory of general relativity, and at its heart was a single, radical idea. Gravity is not a force pulling things toward each other. Gravity is the bending of space itself. Imagine a bowling ball sitting on a trampoline. The ball is heavy. It creates a dip, a curve, a warp in the fabric of the trampoline. Now roll a marble across the surface. The marble does not go in a straight line. It curves toward the dip. It follows the shape of the trampoline. That is gravity. Mass bends space, and everything that moves through that space follows the curves. Now here is the key. Light follows those curves too. Light always travels in a straight line. But if space itself is bent, then the straight line through bent space looks curved to us. This means that when light from a distant galaxy passes near a massive object, like a cluster of galaxies, the light bends. Its path is warped. The image of the distant galaxy is stretched, distorted, magnified. Sometimes it is smeared into arcs. Sometimes it appears in multiple copies. This is called gravitational lensing. It is one of the most powerful tools in all of astronomy. And here is why it matters for dark matter. The bending of light does not care whether the mass is visible or invisible. Mass is mass. Gravity does not check if you glow. A clump of dark matter bends light just as effectively as a clump of stars. So if you look at the images of distant galaxies and you notice that they are slightly stretched, slightly warped, slightly out of shape, you can work backward. You can figure out where the mass is that caused the distortion, even if you cannot see that mass, even if it is completely invisible. The distortion in the light is like a fingerprint left at a crime scene by a ghost. You cannot see the ghost, but the fingerprint tells you it was there. Now, there are two kinds of gravitational lensing. Strong lensing is dramatic. It creates arcs and rings and multiple images. You can see it with your eyes in a good telescope image. But strong lensing only happens near the most massive objects. Galaxy clusters, enormous concentrations of matter. Most of the universe is not that extreme. Most of the dark matter is spread out in a subtler, more diffuse pattern. And to map that, you need something much more delicate. You need weak lensing. Weak lensing is exactly what it sounds like. It is the tiny, almost imperceptible stretching of galaxy images caused by the gravitational pull of matter along the line of sight. We are not talking about dramatic arcs. We are talking about a galaxy that should look perfectly round looking slightly oval instead, by maybe 1%, maybe less. One galaxy looking slightly oval does not tell you much. It could just be a naturally elongated galaxy. But if you look at thousands of galaxies in the same region, and they all seem to be stretched in the same direction, that is a pattern. That is a signal. That means something in between is warping their light. Something massive. Something invisible. And by measuring that pattern across hundreds of thousands of galaxies, you can build a map. A map of the invisible mass that sits between us and those distant lights. That is exactly what the Cosmos Webb team did. And the instrument they used was the most powerful camera ever pointed at the sky. The James Webb Space Telescope. Let us talk about JWST for a moment, because it is not just any telescope. It is the telescope. It launched on Christmas Day 2021. It traveled 1 million miles from Earth to a spot called L2, a gravitational sweet spot where it orbits the Sun in lockstep with our planet, always in Earth's shadow. Its primary mirror is 21 feet across, made of 18 hexagonal segments coated in gold. Gold, because gold is excellent at reflecting infrared light, the kind of light that travels across the universe from the most distant galaxies. JWST does not see invisible light like Hubble did. It sees in infrared, and that is crucial, because the universe is expanding. As light travels across billions of years, it gets stretched. Visible light shifts into the infrared. To see the most distant, most ancient objects, you need infrared eyes, and JWST has the best infrared eyes ever built. There is something worth pausing on here. The mirror. JWST's primary mirror is the largest mirror ever sent into space, 6.5 meters across, made of beryllium, coated in a layer of gold so thin that if you gathered all the gold on the mirror, it would only fill a marble. But that thin layer of gold is the reason the telescope can see what it sees. Gold reflects infrared light with over 98% efficiency. Every infrared photon that hits that mirror bounces off and into the telescope's instruments. Photons that have been traveling for billions of years. Photons that left their home galaxies when the universe was young. Photons that have been stretched by the expansion of space until their wavelengths have shifted from visible light into the infrared. JWST catches those ancient stretched photons one by one, and from them it reconstructs images of the distant universe with a clarity that would have seemed like science fiction just 20 years ago. The telescope sits behind a sun shield the size of a tennis court, 5 layers of thin, reflective material that block the heat from the sun, the earth, and the moon. Behind that shield, the telescope cools to minus 233 degrees Celsius, nearly as cold as outer space itself. It has to be that cold because infrared light is essentially heat radiation. If the telescope were warm, its own heat would drown out the faint infrared signals from distant galaxies. So it sits in the cold, in the dark, in the silence, listening to the whispers of the ancient universe, patient, precise, unblinking. And it was this extraordinary instrument that scientists turned toward the constellation sextans, toward the cosmos field, toward the emptiest looking patch of sky they could find. Because sometimes, to see the most, you have to look where there appears to be the least. But JWST was not originally designed to map dark matter. Its primary missions involve studying the early universe, looking at the atmospheres of exoplanets, watching stars being born. Dark matter mapping was not the headline goal. And yet, the sheer power of the telescope, its incredible resolution and sensitivity, made it the perfect tool for the job. Because weak lensing requires something very specific. You need sharp, detailed images of enormous numbers of galaxies. You need to measure their shapes with incredible precision, and JWST delivers that precision like nothing before it. The Hubble Space Telescope, JWST's older sibling, could resolve about 71 galaxies per square arc minute. That is a very small patch of sky. JWST can resolve about 129 galaxies in the same area, almost twice as many. And it can see galaxies that are fainter and more distant. That means more data points, more measurements, a sharper picture. Going from Hubble to JWST for dark matter mapping is like going from a blurry old map drawn by hand to a crisp satellite image. And the place they chose to point JWST was not random. It is one of the most studied patches of sky in all of astronomy. A region called the Cosmos field. Cosmos stands for Cosmic Evolution Survey, and this field sits in the constellation Sextans. Sextans is a faint constellation. You probably cannot see it from your backyard. It sits near the celestial equator, below Leo the Lion. There is nothing special about it to the naked eye. No bright stars, no famous patterns. Just a quiet, unremarkable patch of darkness. And that is exactly why scientists chose it. You see, when you want to study the deep universe, you want to look at a spot that is not cluttered with nearby stars. You want a clean line of sight through the cosmos. The Sextans region provides that. It is like looking through a clear window rather than a foggy one. And over the past 20 years, this little patch of sky has become the most important piece of real estate in all of science. More than 15 telescopes, both on the ground and in space, have pointed at the cosmos field. Hubble has stared at it. Ground-based observatories in Chile and Hawaii have photographed it. X-ray telescopes have scanned it. Radio telescopes have listened to it. Layer upon layer of data has been built up, giving scientists a rich, multi-wavelength portrait of this one special region. And now JWST has added the sharpest layer yet. The Cosmos Webb Survey, as it is called, is the largest program undertaken by JWST in its first year of operations. The telescope spent 250 hours, over 10 full days, staring at this one patch of sky. It used its near-infrared camera, called NearCam, to photograph 0.54 square degrees of sky. That is roughly 2.5 times the size of the full moon, as seen from Earth. It does not sound like much, but at the depth and resolution JWST achieves, that small patch contains a staggering amount of information. Nearly 800,000 galaxies in one image. Think about that. 800,000 galaxies, each one containing billions of stars, each star potentially hosting planets, and all of them, every single one, slightly distorted, their shapes subtly warped by the invisible mass sitting between them and us. That distortion, measured across all 800,000 galaxies, is the raw data that the scientists used to build their map. The team was led by Diana Scognamiglio, a postdoctoral researcher at NASA's Jet Propulsion Laboratory, working with collaborators including Gavin Leroy at Durham University and David Harvey. They developed sophisticated mathematical techniques to extract the weak lensing signal from the galaxy shapes. This is not easy work. Imagine trying to detect a 1% change in the shape of an object that is billions of light years away and only a few pixels across in your image. Now imagine doing that for 800,000 objects, accounting for the telescope's own distortions, the effects of the detector, the noise in the data, and the natural variety of galaxy shapes. It is like trying to hear a whisper at a rock concert. But they did it. And the picture that emerged was stunning. The map shows the distribution of dark matter across the cosmos field. Dense regions appear as bright knots. Less dense regions appear as faint filaments stretching between them. And the emptiest regions, the cosmic voids, appear as dark gaps. The overall pattern looks like a web, a vast, intricate, three-dimensional web of invisible matter stretching across the sky. And nestled along the strands of that web, sitting at the intersections, clustered around the densest knots, are the galaxies, the visible matter, the stars and gas and dust, all of it following the invisible scaffolding, all of it arranged by dark matter's gravity. It is as if someone built an enormous frame out of invisible wire, and then all the glitter and paint and ornaments of the universe settled along the wires and collected at the joints. Richard Massey, a physicist at Durham University and one of the study's co-authors, put it simply. He called dark matter the gravitational scaffolding into which everything else falls and is built into galaxies. And we can actually see that process happening in this map. That statement is worth sitting with. We can see it happening. For the first time, we are not just imagining the scaffolding. We are looking at it. The map was published in the journal Nature Astronomy on January 26, 2026, and when it was unveiled, the reaction from the scientific community was electric. Diana Scognamiglio presented a preliminary version of the map at a Cosmos collaboration meeting in May of 2025. She showed it side by side with the original dark matter map that Hubble had made of the same region back in 2007. And as the slide appeared, something remarkable happened. The audience started clapping. Not polite, professional clapping, real clapping, excited clapping, because the structures matched. The same large-scale patterns that Hubble had barely glimpsed were there in the JWST map, but now resolved into finer filaments, sharper peaks, and richer detail. It was like seeing a photograph of a city you had only ever seen in a blurry sketch. The bones were the same, but now you could see the streets. Let us pause for a moment. Let this sink in. We are talking about a map of something invisible, something that no human being will ever touch or hold or see with their eyes. And yet, here it is, drawn on a computer screen, published in a journal, peer-reviewed and confirmed. The invisible has become visible, the hidden has been revealed, and the universe, it turns out, has a skeleton, a framework, an architecture, and we are just beginning to read the blueprints. Now let us go deeper into that architecture. Let us walk through the map. Let us explore what it shows us about the largest structures in the universe. Because the dark matter web is not just a pretty picture. It is the key to understanding how everything got here, how the first galaxies formed, how they grew, how they clustered together, and how the universe evolved from a smooth, featureless cloud of particles into the grand, glittering tapestry we see today. To understand the cosmic web, you need to go back to the very beginning. The very, very beginning. Roughly 13.8 billion years ago, the universe was born in the Big Bang. And in those first moments, everything was smooth, almost perfectly smooth. Matter was spread out evenly in every direction. There were no galaxies, no stars, no planets, just an incredibly hot, dense soup of particles and radiation, expanding in all directions. But that soup was not perfectly smooth. There were tiny ripples, incredibly tiny. We are talking about variations in density of about 1 part in 100,000. In some spots, there was a tiny bit more matter. In others, a tiny bit less. Those tiny ripples are the seeds of everything. and we know they existed because we can see their imprint. The cosmic microwave background, the afterglow of the Big Bang, carries the pattern of those ancient ripples. It is the oldest light in the universe, released about 380,000 years after the Big Bang, and it shows us the baby picture of the cosmos. Tiny warm spots and cool spots, tiny peaks and valleys, almost imperceptible, but they were enough, because gravity is patient, and gravity is relentless. A region with a tiny bit more matter has a tiny bit more gravity. It pulls a tiny bit more material toward it. Over time, that material adds more gravity, which pulls more material, which adds more gravity. It is a snowball effect, a cosmic feedback loop, and dark matter, because it does not interact with light, began this process first. In the earliest epochs, ordinary matter was still tangled up with radiation. Photons bounced off protons and electrons, keeping them from clumping together. But dark matter did not care about photons. It was invisible to light, so it began to collapse under its own gravity, forming the first structures, while ordinary matter was still stuck in the radiation fog. This is the critical point. Dark matter moved first. It built the framework first. It created the first gravitational valleys, the first dips in the fabric of space, before ordinary matter could even begin to follow. And then, about 380,000 years after the Big Bang, the universe cooled enough for ordinary matter to break free from the radiation. The fog cleared, and ordinary matter, suddenly free, looked around and found the gravitational landscape that dark matter had already prepared. It fell into the valleys. It flowed along the ridges. It pooled in the deepest basins. And it began to form the first stars, the first galaxies, the first clusters. This is why dark matter is sometimes called the architect of the universe. It did not just participate in building the cosmos. It drew the blueprints. It laid the foundation. It created the framework. And everything visible, everything we can see and touch and photograph, is just the decoration on top of the invisible structure that dark matter built. And before we dive deeper into the cosmic web itself, there is one more piece of evidence worth knowing about. One more observation that cemented dark matter's place in our understanding of the cosmos. And it came from one of the most violent events ever witnessed. A cosmic collision so massive, so energetic, so devastating, that it actually separated the dark matter from the ordinary matter. And we could watch it happen. It is called the bullet cluster, and it is one of the most important objects in all of cosmology. In 2006, astronomers observed two massive galaxy clusters in the process of smashing into each other. A smaller cluster had punched through a larger one at a speed of several million miles per hour. And in the collision, something extraordinary happened. The hot gas in the clusters, which makes up most of the ordinary matter, slammed together. It collided. It heated up. It slowed down. You can see it in X-ray images. A bright cloud of superheated gas sitting in the middle of the collision zone. But the dark matter did not collide. It did not interact with the gas. It did not slow down. It kept right on going, passing through the collision like a ghost passing through a wall. The weak lensing maps showed that the mass, the gravitational center, was not where the gas was. Origin had separated. It had moved ahead, carried by the dark matter, which passed through the collision without stopping. This was a smoking gun. The ordinary matter was left behind. The dark matter flew ahead. They were separated, and that separation proved that dark matter is not just ordinary matter that we have somehow missed. It is not gas. It is not dust. It is not failed stars. It is something different, something that does not collide with itself or with ordinary matter. something that only interacts through gravity. The bullet cluster was the moment the scientific debate effectively ended. Dark matter is real. It is not ordinary matter in disguise. It is a new form of matter. And the 2026 Cosmos Webb map is the latest and most detailed chapter in the story that the bullet cluster helped begin. Now, with that foundation in place, let us look at the structure dark matter built. Now, the structure that dark matter built has a specific shape, and it is not random. It is not a uniform fog or a featureless blob. It is a web. Scientists call it the cosmic web, and the 2026 map from JWST shows it in more detail than ever before. Picture this. Imagine you could shrink the entire observable universe down to the size of a room. If you could somehow see all the dark matter at once, you would see something that looks remarkably like a sponge, or a network of soap bubbles, or the neural network inside a brain. There are long, thin filaments stretching across the void. At the places where filaments cross, there are thick knots of matter, dense clusters where thousands of galaxies gather together. Between the filaments, there are vast, empty regions called voids, enormous bubbles of near-nothingness that can stretch for hundreds of millions of light years. And connecting everything, weaving it all together, are sheets, thin walls of dark matter that form the surfaces between voids. Filaments, nodes, sheets, and voids. Those are the four building blocks of the cosmic web. And every galaxy you have ever seen in a photograph, every galaxy that has ever been named or studied or wondered about, sits somewhere on this web. Most galaxies live in or near filaments. The biggest galaxies, the brightest clusters, sit at the nodes. And the voids are among the emptiest places in all of existence. Some voids are so large that light would take hundreds of millions of years to cross them. And inside those voids, there is almost nothing. A few lonely galaxies perhaps, some thin wisps of gas, but mostly just space. Cold, empty, silent space. The cosmic web is the largest structure in the universe. Larger than any galaxy. Larger than any supercluster. It extends as far as our telescopes can see, in every direction. And it was built, all of it, by dark matter. The JWST map reveals this web in the cosmos field with extraordinary clarity. Previous maps, made by Hubble and ground-based telescopes, could see the broad outlines, the biggest clusters, the thickest filaments. But the details were fuzzy. It was like looking at a road map from far away. You could see the major highways, but not the side streets. JWST changed that. The resolution of the new map is 1 arc-minute. That is more than twice as sharp as any previous space-based dark matter map of a comparable area. And with that sharpness, structures that were previously invisible suddenly snapped into focus. For the first time, scientists could see the dark matter halos around small groups of galaxies. Not just the giant clusters, small groups. Collections of maybe a dozen galaxies, bound together by a shared clump of dark matter. These small structures were completely invisible in the Hubble map. They were below the threshold of detection. But JWST's superior sensitivity, its ability to resolve 129 galaxies per square arc-minute compared to Hubble's 71, brought them into view. It is like upgrading from a standard definition television to a 4K screen. The picture is the same, but now you can see the details. And the details matter, because the details tell us how dark matter behaves on smaller scales. And how dark matter behaves on smaller scales is one of the biggest open questions in physics. On the larger scales, the theory works beautifully. The standard model of cosmology, called lambda CDM, predicts the cosmic web perfectly. It predicts the cosmic microwave background with stunning precision. It tells us that the universe is 5% ordinary matter, 27% dark matter, and 68% dark energy. And when we look at the biggest structures in the universe, the theory matches the observations. But on smaller scales, things get more complicated. Computer simulations based on lambda CDM predict that dark matter halos should have a very specific shape. They should be dense in the center and gradually less dense toward the edges. This is called a cuspy profile. But when we look at actual dwarf galaxies, the smallest galaxies we can observe, some of them seem to have flatter, chord density profiles. The dark matter in their centers appears to be less concentrated than the simulations predict. This is called the cusp core problem. There are also too few small galaxies. Simulations predict that every large galaxy should be surrounded by hundreds, maybe thousands, of tiny satellite galaxies, each hosted by its own dark matter halo. But we see far fewer than predicted. This is called the missing satellites problem, and there is a related puzzle called the too big to fail problem. Some of the most massive predicted satellites are so big that they should have easily formed visible galaxies. But we do not see them. They seem to have failed to form stars, or they do not exist at all. These small-scale puzzles are not necessarily fatal to the dark matter theory. Most scientists believe they can be explained by ordinary astrophysics, the messy, complicated processes of gas cooling, star formation, and supernovae explosions that can rearrange the dark matter in small galaxies. But the possibility remains that these discrepancies are telling us something deeper, something about the nature of dark matter itself. Maybe dark matter is not perfectly cold and collisionless, as lambda CDM assumes. Maybe dark matter particles have some tiny, subtle interaction with each other. Maybe they are not WIMPs at all, but something else entirely. Axions, perhaps, or fuzzy dark matter, or primordial black holes. The list of candidates grows longer each year. This is where the 2026 map becomes a vital new tool. By measuring the dark matter distribution on smaller scales than ever before, the JWST map provides new data to test these theories. If the map matches the lambda CDM predictions perfectly, down to the smallest structures, that tells us one thing. If there are discrepancies, if the filaments are thicker or thinner than expected, if the small halos are shaped differently than the simulations predict, that tells us something entirely different. It tells us the standard model might need updating. It tells us there might be new physics hiding in the dark. And there are already hints that something interesting is going on. In early January of 2026, just weeks before the dark matter map was released, a separate study published in Nature Astronomy found evidence that dark matter and neutrinos might actually interact with each other. Neutrinos are the lightest known particles. They are almost massless. They barely interact with anything. And yet, the study, led by researchers at the University of Sheffield, found signs that dark matter and neutrinos might have influenced each other in the early universe. If confirmed, this would be a groundbreaking discovery. It would mean that dark matter is not as isolated as we thought. It would mean the standard model of cosmology, lambda CDM, might need to be revised, and it could point the way toward finally understanding what dark matter actually is. But we are getting ahead of ourselves. Let us come back to the map. Let us come back to the cosmos field. Let us come back to that quiet patch of sky in the constellation sextans. What did the map actually show? What did the scientists see when they looked at the invisible universe through the lens of 800,000 galaxies? They saw filaments, long, thin threads of dark matter stretching across the field, connecting dense regions to each other. These filaments are not just theoretical constructs or computer simulations. They are real. They are there, mapped from actual data. And along those filaments, like beads on a string, sit the galaxies. Ordinary, visible, glowing galaxies, strung out along the invisible threads of dark matter, following the framework, obeying the architecture. They saw clusters, dense knots where filaments intersect. These are the cosmic cities, the grand hubs where thousands of galaxies gather, where the dark matter is thickest, where the gravitational pull is strongest. Some of these clusters were already known. Scientists had mapped them using X-ray telescopes and optical surveys, but the JWST map showed them with new precision. The dark matter contours wrapped tightly around the galaxy, clusters, matching their positions almost exactly. Dark matter and visible matter, locked together in the same cosmic embrace. They saw voids, regions of low density, where the dark matter is thin and the galaxies are scarce. These voids appear as pale gaps in the map, stretching between the filaments like the spaces between the strands of a spider web. And they saw something new, something that had never been detected before. Small groups of galaxies surrounded by their own dark matter halos that were too faint and too distant to appear in any previous map. These are the cosmic villages, small collections of galaxies bound together by modest amounts of dark matter, sitting along the filaments far from the major clusters. Their discovery tells us that the cosmic web is even richer and more detailed than we knew. It is not just highways and cities. It is highways and cities and small towns and rural communities. Every scale of structure, from the grandest to the humblest, is shaped by dark matter. The comparison between the 2007 Hubble map and the 2026 JWST map is particularly striking. Both maps cover the same region of sky. Both use weak gravitational lensing. But the difference in quality is dramatic. The Hubble map is like an impressionist painting. You can see the general shapes, the broad strokes, the suggestion of structure. The JWST map is like a photograph, sharp, detailed, precise. And when you overlay one on top of the other, the same large structures appear in both. The same major clusters, the same biggest filaments. This is an important confirmation. It tells us that the technique works, that we are not just seeing noise or artifacts. The invisible structure is real, it is consistent, and it is now visible in unprecedented detail. But the JWST map also reveals things the Hubble map could never show. Fine filamentary connections between clusters, small halos that were completely below Hubble's detection limit, subtle variations in the density of the web that hint at how dark matter has clumped and flowed over billions of years. Each new detail is a new piece of the puzzle, a new clue about how the universe works. Let us zoom in even further. Let us think about what is happening inside those filaments. Because the cosmic web is not static. It is not a frozen structure. It is alive. It is evolving. Matter is still flowing along the filaments, streaming toward the clusters, feeding the ongoing growth of the universe's largest structures. Gas flows along the dark matter filaments, heating up as it falls into the gravitational wells. Where the gas is densest and hottest, stars form, galaxies grow, clusters get more massive. The cosmic web is not just a structure, it is a highway system, a cosmic circulatory network that feeds the growth of everything. And the gas in those filaments has actually been observed directly. In 2024, a team of researchers captured the first high-definition image of a cosmic filament connecting two galaxies. The filament, stretching across 3 million light-years, was glowing faintly in the light of hydrogen gas. The observation, published in Nature Astronomy, matched the predictions of supercomputer simulations almost perfectly. The gas was flowing along the dark matter thread, feeding the galaxies at either end. The circulatory system was working. The cosmic plumbing was real. Now let us pull back again. Let us think about the bigger picture. What does the 2026 map tell us about the fundamental nature of dark matter? This is the question that keeps physicists up at night. Not just where is dark matter, but what is it? We know several things for certain. Dark matter has mass. It interacts with gravity. It does not interact with light. It does not interact with the electromagnetic force. It does not interact with the strong nuclear force. It appears to be stable, lasting for the entire age of the universe without decaying. And it appears to be cold, meaning the particles move slowly compared to the speed of light. This rules out ordinary neutrinos, which are too hot, too fast, too light. It rules out any known particle. Whatever dark matter is, it is something new, something beyond the standard model of particle physics. The standard model is one of the greatest achievements of the human mind. It describes all the fundamental particles we know about: quarks, leptons, bosons, the Higgs. It predicts the behavior of matter and energy with breathtaking precision. But it is incomplete. It says nothing about dark matter. It says nothing about dark energy. It does not explain why the universe has more matter than antimatter. It does not incorporate gravity. For all its power, the standard model describes only about 5% of what the universe is actually made of. The rest is a blank page, and the 2026 dark matter map is writing on that page, not with words, with data, with the shapes and contours and densities of the invisible web. Because the precise way dark matter is distributed, the exact shape of its halos, the width of its filaments, the depth of its voids, these details depend on what dark matter is. Different dark matter candidates produce slightly different cosmic webs. If dark matter is made of cold, heavy WIMPs, the web looks one way. Dense, cuspy halos. Lots of small satellite structures. Sharp edges. If dark matter is made of ultralight axions, sometimes called fuzzy dark matter, the web looks slightly different. The smallest structures are smoothed out. The densest cores of halos are flatter. The filaments are a little thicker, a little less sharp. If dark matter interacts with itself, even a tiny bit, the web changes again. The cores of halos become even flatter. Satellite galaxies are disrupted. The smallest structures dissolve. Each theory predicts a slightly different web, and the more precisely we can map the web, the better we can distinguish between those theories. The 2026 map is not yet precise enough to definitively rule out any candidate, but it is the sharpest picture we have, and it is pushing the boundaries of what we can test. Scientists are already comparing the map to the latest computer simulations, looking for matches and mismatches, clues and discrepancies. Every pixel of that map is a data point. Every data point is a test of our understanding of the cosmos. And there is another piece of this puzzle that makes the 2026 map particularly powerful. It does not just show us where dark matter is right now. It shows us where dark matter was in the past. Because the galaxies in the Cosmos Web Survey are at different distances. Some are relatively nearby. Some are billions of light years away. And because light takes time to travel, looking at distant galaxies is like looking back in time. A galaxy that is 10 billion light years away is being seen as it was 10 billion years ago. The light only just reached us. This means the map contains a time component. The dark matter distribution is not just a snapshot. It is a movie, a time lapse of how the cosmic web, has evolved over billions of years. The team traced features out to a redshift of about 2, which corresponds to a time when the universe was roughly 3 to 4 billion years old, roughly a quarter of its current age. They could see how the dark matter structures were smaller and less developed in the early universe, and how they grew and connected over time to form the grand web we see today. Watching the cosmic web grow is like watching a city being built in fast forward. First, there are scattered settlements, small clusters, isolated pockets of density. Then roads begin to appear, connecting the settlements. The roads thicken. More settlements spring up along them. Intersections become hubs. Hubs become cities. And eventually, a vast metropolitan network stretches from horizon to horizon. That is the cosmic web. And the 2026 map lets us watch it being built. This is profoundly important for testing our theories. Lambda CDM makes very specific predictions about how fast the cosmic web should grow, how quickly filaments should form, and how dense clusters should become at different epochs. If the map shows the web growing at the right pace, Lambda CDM is confirmed. If the web grew too fast or too slow, something is wrong with our model. And finding what is wrong could lead us to what is right, could lead us to the truth about dark matter. And there are independent checks on this. The cosmic microwave background, the baby picture of the universe, tells us what the initial conditions were. The dark matter map tells us where those initial conditions led. And in between, the physics of gravity and dark matter connects the two. If we start with the cosmic microwave background and run a simulation forward, using Lambda CDM, do we get the map? If yes, our model works. If no, we need a new one. This is the most powerful test of cosmology that we have. So let us take a walk through the cosmic web. Let us imagine we could shrink ourselves down and fly through the 2026 map. Let us start at one of the dense nodes, a cluster of galaxies, one of the great cosmic cities. You approach it from a distance. At first you see nothing special, just the usual scattering of faint galaxy light. But as you draw closer, you begin to feel the gravity. Not with your body, of course, but with the light around you. The photons from distant galaxies behind the cluster are beginning to curve. Their paths are bending. Their images are stretching. You are entering the gravitational field of something enormous. And as you move deeper, you begin to see the galaxies gathering. Not in random positions. They are clustered along invisible rails, invisible highways of dark matter that converge on this central knot. And then you are in the heart of the cluster, surrounded by hundreds, maybe thousands of galaxies. Elliptical galaxies mostly, their stars old and red, their gas long since consumed. These are the ancient residents of the densest neighborhoods in the universe. They have lived here for billions of years, trapped in the gravitational embrace of the dark matter that holds the cluster together. The dark matter here is thick, dense, a massive halo weighing trillions of times the mass of the sun, enveloping the entire cluster. You cannot see it, but you can feel its weight in the way light bends around you, in the way the galaxies move, in the way everything is pulled toward the center. Now you turn and begin to follow one of the filaments, a long thread of dark matter stretching away from the cluster, reaching toward the next node. You leave the crowds behind, the galaxies thin out. But they do not disappear entirely. Along the filament, spaced at intervals, you see galaxies, spiral galaxies, many of them, their arms bright with young blue stars. They are like small towns along a country road, connected by the invisible highway of dark matter, but far from the metropolitan core. Gas is flowing along this filament. You can imagine it if you close your eyes. a slow, steady river of hydrogen streaming along the dark matter thread, feeding the galaxies it passes. Some of this gas will collapse and form stars. Some will be heated to millions of degrees by the shock of falling into the gravitational well. Some will simply flow onward toward the next cluster. The filament stretches on and on, millions of light years, tens of millions. You are crossing a distance that light itself takes millions of years to traverse. And all around you, the dark matter is there, thin compared to the cluster, but present, always present, a gentle gravitational valley guiding the flow of matter across the cosmos. And then you reach the edge of a void. The filament ends, or rather, it meets a wall, a thin sheet of dark matter that forms the boundary of an enormous empty region. You pause at the edge and look in. The void stretches before you in every direction. It is enormous, hundreds of millions of light years across, and inside there is almost nothing. A few lonely galaxies drifting in the emptiness, but mostly just space. Quiet, cold, empty space. The silence of the void is profound. This is the emptiest place you have ever been. And yet, even here, dark matter exists. It is thin, diluted, barely a whisper of gravitational influence. But it is there. The web has no true edges. It fades, but it never vanishes. Standing at the edge of this void, you realize something. You are looking at the negative space of the universe, the holes in the sponge, the gaps in the web. And those gaps are not just empty, they are shaped. They were carved by the same gravitational processes that built the filaments and clusters. As matter flowed toward the dense regions, it left the voids behind. The voids grew as the web grew. They expanded as the filaments tightened. They are the mirror image of the structure, the yin to the web's yang. And in the 2026 map, they are visible too. Pale, low-density regions between the bright filaments. Each void a testament to the power of gravity. Each gap a signature of the invisible architect. Now let us fly back to the big picture. Let us think about what this map means for the future. Because the Cosmos Web dark matter map is not the end of the story. It is the beginning. It is the first high-resolution page of an atlas that will eventually cover the entire sky. Right now, the JWST map covers just 0.54 square degrees, 2.5 full moons. That is incredibly detailed, but it is a tiny fraction of the sky. The full sky is over 40,000 square degrees. We have mapped dark matter in a patch about 1/100,000th of the total. There is so much more to see, and the next generation of telescopes is already working on it. The European Space Agency's Euclid telescope launched in July 2023. Its mission is to map the dark universe on a grand scale, while JWST looks at a tiny patch in exquisite detail. Euclid will survey a third of the entire sky. By 2030, it will have photographed billions of galaxies. Its first cosmology data will be released in October of 2026, just months from now. And its weak lensing measurements will produce dark matter maps covering areas thousands of times larger than the Cosmos Web field. But Euclid trades resolution for coverage. Its images are not as sharp as JWST's. It can see the broad strokes of the dark matter, web, the major filaments and clusters, but not the fine details, not the small groups and faint halos that JWST revealed. The two telescopes are complementary. JWST is the microscope. Euclid is the wide-angle lens. Together, they give us both the close-up and the panorama. And then there is the Nancy Grace Roman Space Telescope, named after NASA's first chief of astronomy, the woman who championed the Hubble Space Telescope. Roman is expected to launch in late 2026 or 2027, it will carry a camera with a field of view 100 times larger than Hubble's. It will survey the sky with a sensitivity and resolution that falls between Euclid's wide angle and JWST's sharp focus. Roman will map dark matter over enormous areas with better detail than Euclid, but not quite as sharp as JWST. It will fill in the middle ground, the suburbs of the dark universe, to continue our city analogy. And there is one more telescope worth mentioning: the Vera C. Rubin Observatory, named after the woman who gave us the first compelling evidence for dark matter in galaxies. The Rubin Observatory sits on a mountaintop in Chile. It released its first images in 2025, and over the next decade, it will conduct the legacy survey of space and time, photographing the entire visible southern sky every few nights. Its massive camera will detect billions of galaxies, and its data will be used to create the most complete ground-based dark matter maps ever made. Together, these four observatories, JWST, Euclid, Roman, and Rubin, represent a golden age of dark matter science. We are not just hunting for a particle anymore. We are mapping the entire invisible universe. We are building an atlas of the dark, and the 2026 Cosmos Web Map is the first detailed page. But there is a deeper question lurking beneath all of this, a question that goes beyond maps and measurements and telescopes, a question that touches something more fundamental, more personal, more human. And it is this: why does the invisible matter more than the visible? Think about what we have learned. The visible universe, everything you can see, every star and galaxy and nebula, is just 5%. The dark matter web, invisible and untouchable, is 5 times more massive. And it is the dark matter that built the framework, that drew the blueprints, that guided the formation of galaxies and clusters and the cosmic web itself. Without dark matter, there would be no cosmic web. Without the cosmic web, gas would not have collected into dense enough regions to form stars. Without stars, there would be no planets. Without planets, there would be no Earth. Without Earth, there would be no you. You owe your existence to something you cannot see. Your body is made of atoms that were forged in stars, that were born in galaxies, that were shaped by dark matter. The calcium in your bones, the iron in your blood, the oxygen in your lungs, all of it was created in stellar furnaces that exist only because dark matter built the gravitational cradles in which those stars were born. You are a byproduct of the invisible web, a side effect of the dark architect's work. And there is something profoundly beautiful about that, something humbling. It means the universe is deeper than it looks. It means reality extends far beyond what our senses can perceive. Every time you look up at the night sky, you are seeing only the thinnest layer, the frosting on a cake that is made almost entirely of invisible ingredients. And the cake itself, the dark matter scaffolding, is the part that actually holds everything together. The frosting is pretty, but it is the cake that matters. Let us think about this from another angle. Imagine an architect building a skyscraper. The finished building is covered in glass and steel. It has lights and signs and logos. People notice the exterior. They admire the design. They take photographs of it. But underneath all of that, hidden inside the walls, there is a skeleton. Steel beams, concrete pillars, load-bearing structures that carry the weight of every floor above. Nobody sees the skeleton. Nobody photographs it. But without it, the building would collapse in seconds. The skeleton is not decorative. It is not optional. It is the reason the building stands. Dark matter is the skeleton. The stars and galaxies are the glass and lights. and the skeleton was there first. Scientists are beginning to see this architecture in action. The Cosmos Webb map shows that everywhere the dark matter is densest, there are galaxies. Everywhere the dark matter forms a filament, galaxies line up along it. Everywhere the dark matter thins out, galaxies disappear. The correlation is not perfect. There is scatter, there is noise, but the overall pattern is unmistakable. Dark matter leads, visible matter follows. The scaffolding goes up first. The walls and windows come later. This relationship between dark and visible matter is called the galaxy halo connection, and it is one of the most active areas of research in modern cosmology. Scientists want to understand exactly how galaxies form inside dark matter halos, how the properties of a galaxy, its size, its mass, its star formation rate, its shape, are determined by the properties of the dark matter halo that hosts it. The Cosmos Webb map, with its unprecedented resolution, provides new data to study this connection. It shows us the dark matter halos and the galaxies simultaneously in the same frame, allowing direct comparison. And there is an even bigger ambition on the horizon. Scientists are working on creating a three-dimensional version of the Cosmos Webb dark matter map. The current map is two-dimensional. It shows the dark matter projected onto the sky, flattened into a single plane. But the real universe is three-dimensional. The dark matter web has depth. Filaments extend toward us and away from us. Clusters sit at different distances. To truly understand the web, we need to see it in 3 dimensions. And that requires knowing the distances to the galaxies, not just their positions on the sky. This is where the multi-wavelength nature of the cosmos field becomes so valuable. Because so many telescopes have observed this region, scientists have excellent distance measurements for hundreds of thousands of galaxies. They can slice the data by distance, creating a series of maps at different depths, like slicing a loaf of bread. Each slice shows the dark matter at a different cosmic epoch, and when you stack those slices together, you get a 3-dimensional picture, a volumetric map of the invisible universe. This is the next step, and it is already underway. Let us think about one more aspect of the 2026 map before we begin to bring this journey to a close. And it is perhaps the most thought-provoking aspect of all. It has to do with what the map does not show us, what is still missing, what remains hidden even in the most detailed dark matter atlas ever created. Because here is the thing, the map tells us where dark matter is, it tells us how much there is, it tells us how it is distributed, but it does not tell us what it is. The map is like a fingerprint at a crime scene. It tells you that someone was there. It tells you the shape of their fingers, but it does not tell you their name. The fundamental nature of dark matter remains unknown. Is it a particle? Is it many particles? Is it something stranger? Is it a modification of the laws of gravity rather than a new form of matter? The map narrows the possibilities, but it does not close the case. And this is where the marriage of astronomy and particle physics becomes so important. Astronomers can map the dark matter from above. They can trace its outline, measure its density, follow its filaments across the sky. But to truly identify it, we may need a detection from below, a signal in a detector, a particle captured in a tank of liquid xenon, a flash of light from an axion converting into a photon, or perhaps a signal at the Large Hadron Collider, where protons smash together at nearly the speed of light and exotic particles briefly flicker into existence. The search continues. On all fronts, underground detectors are getting more sensitive. Axion experiments are scanning new frequency ranges. The Large Hadron Collider is running at higher energies, and now the astronomers have given the particle physicists a sharper picture to aim for. The map says, look here. The dark matter is thickest along these filaments. Its halos have these shapes. Its distribution follows these patterns. Use this information. Let it guide your search. The invisible has been drawn. Now find the thing that is drawing it. And there is one more experiment, arguably the most ambitious of all. It is not a telescope or a particle detector. It is the universe itself. Because the cosmic web is not just a record of the past. It is an ongoing experiment. Dark matter is still pulling, still shaping, still building. Galaxies are still flowing along filaments. Clusters are still growing. Voids are still expanding. The web is still evolving. And by watching it evolve, by comparing the cosmic web at different points in time, we can learn about the properties of dark matter in ways that no other experiment can match. If dark matter particles decay over time, the web should change. If dark matter interacts with itself, the smallest structures should slowly dissolve. If dark energy is changing, the growth of the web should accelerate or slow down. The universe is the experiment, and the dark matter map is the datasheet. Every filament is a test. Every void is a control group. Every cluster is a measurement. And we have only just begun to read the results. This is the new era that the 2026 map has launched. An era where we do not just search for dark matter. We survey it. We map it. We watch it. We measure its behavior and compare it to our theories. The hunting phase is ending. The surveying phase has begun. And the map is the turning point. The moment we went from searching for a needle in a haystack to drawing a picture of the entire haystack. Let us bring this journey home. Let us come back to where we started, to the telescope floating in the cold silence of space, to the 800,000 galaxies it photographed, to the invisible web it revealed, and to the profound question at the heart of it all. What is the universe made of? We still do not have a complete answer. We may not have one for decades, but we are closer than we have ever been. The 2026 Dark Matter Map is a landmark, a milestone, a monument to human curiosity and ingenuity. It is the first time we have looked at the universe and seen not just the things that shine, but the things that do not. Not just the visible, but the invisible. Not just the matter, but the dark. And in that map, there is a message. A message about the nature of reality, about the structure of existence, about our place in the cosmos. The message is this: you are connected to everything, not metaphorically, not poetically, physically, gravitationally. The dark matter web that stretches across the cosmos, the same web that holds clusters of galaxies together, the same web that feeds gas into star-forming regions, the same web that built the Milky Way. That web reaches all the way to you. You are sitting on it right now. You are embedded in it. You are part of it. The Earth sits in the outskirts of the Milky Way galaxy. The Milky Way sits in a small group of galaxies called the local group. The local group sits near the edge of a larger structure called the Virgo supercluster. And the Virgo supercluster is itself just one small node in the cosmic web. A small town in the grand metropolitan network of the invisible universe. And the filament of dark matter that connects us to the Virgo cluster, the thread that links our little corner of the cosmos to the larger web, is the same kind of structure that the JWST just mapped in the cosmos field. The same kind of filament, the same kind of scaffolding. We are looking at our own neighborhood's cosmic DNA. This is the connection that the 2026 map makes so vivid. It bridges the gap between the abstract and the personal. between the scientific and the emotional, between the data and the wonder. When you see a blue contour on the dark matter map, you are seeing the same kind of structure that holds you in place. The same invisible glue that keeps the Milky Way from flying apart. The same gravitational web that gathered the primordial gas that eventually became the sun, the earth, the oceans, the forests, and you. You were born inside the web. You live inside the web. And when you look up at the night sky, you are looking along the threads of the web. Every photon of starlight that reaches your eye has traveled through the web, bent ever so slightly by the invisible mass along the way. Even your view of the sky is shaped by dark matter. And so, the question changes. It started as, is dark matter there? Fritz Zwicky answered that in 1933. Yes, it is there. Then it became, is it everywhere? Vera Rubin answered that in the 1970s. Yes, it is everywhere. Then it became, what does it look like? The Cosmos Web Map answered that in 2026. It looks like a web, a vast, intricate, beautiful web. And now the question is, what is it doing? Not just where it is, but how it works, how it shapes galaxies, how it feeds star formation, how it evolves over time, how it connects the smallest structures to the largest, how it bridges the gap between quantum physics and cosmology. The question has shifted from presence to process, from is it there to what is it doing? And answering that question will be the work of the next generation of scientists, telescopes, and maps. Let us go even deeper now. Let us think about what the cosmic web looked like when it was young, because the 2026 map does not just show us the web as it is today. It gives us glimpses of the web as it was billions of years ago. And those glimpses tell a story of creation that is almost unimaginable in its scale. Go back in your mind to a time about 13.8 billion years ago. The universe has just been born. It is a fraction of a second old, and it is unrecognizable. There are no atoms yet, no stars, no galaxies, just an inconceivably hot, dense, expanding fireball of energy and subatomic particles. Quarks and gluons and photons and neutrinos, all crammed together in a space so small and so hot that the laws of physics as we understand them barely apply. But even in this chaos, something is already happening. The dark matter is there. From the very first moments, it does not interact with the light. It does not feel the heat. It simply responds to gravity. And as the universe expands and cools, the dark matter begins to separate from the radiation. It begins to drift, to flow, to feel the tiny gravitational tugs created by those primordial density fluctuations, the tiny ripples in the fabric of the newborn cosmos. Over the next few 100,000 years, while ordinary matter is still locked in its dance with photons, dark matter is quietly building. Tiny overdensities attract more dark matter. Small clumps grow into larger clumps. The seeds of the cosmic web are being planted in the dark, long before the first ray of starlight will ever shine. Then comes a moment of liberation. About 380,000 years after the Big Bang, the universe cools enough for electrons to combine with protons, forming neutral hydrogen atoms. The photons, no longer bouncing off free electrons, stream away in all directions. This is the moment we call recombination, and it is the moment when the cosmic microwave background is released. The oldest light in the universe, traveling through space for 13.8 billion years until it reaches our detectors today. And once the photons are gone, ordinary matter is free. It can finally feel the gravitational landscape that dark matter has been quietly sculpting. And it falls. Gas streams into the dark matter valleys. It pools in the deepest wells. It begins to cool, to compress, to fragment, and within a few 100 million years, the first stars ignite. These first stars are unlike anything that exists today. They are enormous, hundreds of times the mass of our sun, burning furiously, bright and blue and violent. They live fast and die young, exploding as supernovae, scattering newly forged elements into the gas around them. Carbon, oxygen, silicon, iron, the elements that will one day make planets and people and everything in between. And where are these first stars born? Along the filaments of the cosmic web, in the small, dense dark matter, halos that form the earliest nodes. Think about that. The very first light in the universe was born on the scaffolding of dark matter. The first fires were lit along the invisible threads. The cosmic web did not just build the structure of the universe. It built the chemistry. It built the conditions for complexity. It built the stage on which every act of cosmic creation has played out since. As the eons passed, the web grew. Small halos merged to form larger halos. Filaments thickened. Nodes attracted more and more matter. Galaxies formed, grew, merged with other galaxies. The universe became more complex, more structured, more beautiful. And through it all, dark matter was the quiet backbone, the hidden spine of everything. The 2026 map captures this evolution in a remarkable way. Time, Guans. Because the Cosmos Web Survey includes galaxies at many different distances, it sees the web at many different times. Nearby galaxies show the web as it looks today, mature and fully formed. Distant galaxies show the web as it was billions of years ago, younger and less developed. By comparing these different epochs, scientists can watch the web grow. They can see filaments forming. They can see clusters assembling. They can see the cosmic skeleton becoming more defined and more complex over time. This is not idle curiosity. This is one of the most powerful tests of our cosmological model that exists. Lambda CDM predicts exactly how fast the web should grow. It predicts how dense the clusters should be at different epochs. It predicts the distribution of filament lengths and void sizes at every stage of the universe's history. Time channel ones. If the observations match the predictions, Lambda CDM is confirmed. If they do not, something is wrong with our understanding of dark matter, dark energy, or both. And there are already tensions, small ones, subtle ones, but real ones. One of the most discussed is called the S8 tension. S8 is a number that describes how clumpy the universe is, how strongly matter clumps together on large scales. The cosmic microwave background, which gives us the initial conditions, predicts a certain value of S8. But when scientists measure the actual clumpiness of the universe today, using galaxy surveys and weak lensing, they sometimes find a slightly lower value. The universe appears to be a little less clumpy than it should be, a little smoother, a little less structured. This discrepancy is small. It is not definitive. It could be a statistical fluke. It could be caused by systematic errors in the measurements. But it could also be real. And if it is real, it could be pointing to new physics. Perhaps dark matter is not perfectly cold. Perhaps it has a tiny amount of warmth, a slight velocity that prevents it from clumping as tightly as Lambda CDM predicts. Perhaps dark energy is not constant but changing over time. Perhaps dark matter and neutrinos are interacting, as that early 2026 study suggested, subtly suppressing the growth of structure. The Cosmos Web dark matter map provides fresh data to address this question. By measuring the clumpiness of dark matter directly, through weak lensing, in a well-studied field with excellent photometric data, the team can make an independent measurement of S8, and they can compare it to the predictions. This comparison is ongoing. The results will take time, but the data is there. The map is there. And every scientist in the field is watching. There is another tension worth mentioning, a bigger one. It is called the Hubble tension. And while it is not directly about dark matter, it is connected to the same web of cosmic measurements. The Hubble constant, h(0), measures how fast the universe is expanding today. There are two main ways to measure it. One uses the cosmic microwave background and assumes lambda CDM, extrapolating from the early universe to today. The other uses direct measurements of nearby objects, like supernovae and Cepheid variable stars, to measure the expansion rate right now. And they do not agree. The direct method gives a higher value. The early universe method gives a lower value. The gap between them is significant enough that it is unlikely to be a coincidence. Something is off. Some researchers think the Hubble tension could be pointing to new physics beyond lambda CDM. Perhaps dark energy is evolving. Perhaps there was an extra burst of energy in the early universe. Perhaps the properties of dark matter are different from what we assume. Or perhaps the measurements themselves have hidden errors that we have not yet identified. The answer is not clear. But the dark matter map, by providing an independent window into the growth of structure, adds another piece of evidence, another data point, another constraint. It is one more clue in the greatest cosmic detective story ever told. Let us shift now. Let us move away from the tensions and controversies and think about something simpler, something more personal. Let us think about what it feels like to look at this map, to really look at it, to sit with it. Imagine you are in a dark room. You are sitting in front of a large screen. On the screen is the Cosmos Webb dark matter map. The background is dark. The galaxies are tiny points of light, hundreds of thousands of them, scattered across the field like grains of sand. And overlaid on top of those galaxies, in translucent blue, is the dark matter. The densest regions glow bright blue. The filaments are fainter, like wisps of blue fog stretching between the bright knots, and between the filaments, the voids are almost empty. Dark, quiet. You stare at it, and at first, it looks like a pattern, a web, a network, something organized, something purposeful. But as you keep looking, it begins to feel like something more. It begins to feel alive. The filaments look like blood vessels. The nodes look like organs. The voids look like lungs. The whole thing looks like a living thing, a vast cosmic organism, pulsing with invisible energy, threaded with invisible matter, stretching across space and time in a way that defies comprehension. And then a thought strikes you. This is the thing that made me. This invisible web, this dark matter scaffolding, this hidden architecture of the cosmos. This is the thing that gathered the gas that became the sun, that formed the Milky Way, that created the conditions for Earth, that built the stage on which life emerged. You are looking at your own creator, not a being, not a deity, not a conscious agent, but a structure, a process, a set of physical laws playing out over 13.8 billion years, weaving a web so vast and so intricate that it eventually, in one tiny corner, in one small galaxy, on one modest planet, gave rise to a species that could build a telescope and look back at the web that made it. That is the miracle, not a supernatural one, a natural one, a physical one. The miracle is that the universe is not just beautiful, it is knowable, it is measurable, it is mappable, even the parts we cannot see. Now let us think about the sextans field itself, this quiet little patch of sky where the map was made. Sextans is one of the dimmest constellations in the sky. It was defined in the late 1600s by the Polish astronomer Johannes Hevelius. He named it after the sextant, the navigational instrument he used in his observatory. It is a fitting name, because a sextant is a tool for finding your position. And that is exactly what the cosmos field in sextans is doing for us. It is helping us find our position in the universe. Not our physical position, our conceptual position, our understanding of where we are in the grand scheme of things. The cosmos field was first established in the early 2000s. A team of astronomers selected this region because it offered a clean, unobstructed view of the deep universe. It was far from the plane of the Milky Way, where dust and stars would clutter the view. It was accessible to telescopes in both the northern and southern hemispheres, and it was large enough to capture a representative slice of the cosmic web. Over the next 2 decades, more than 15 telescopes contributed data to the cosmos field. Hubble made the original map. Ground-based telescopes in Hawaii and Chile added depth. X-ray observatories mapped the hot gas in galaxy clusters. Radio telescopes detected the faint emission of hydrogen gas. And now, JWST has added the sharpest layer of all. The result is one of the most thoroughly studied regions in all of astronomy. We know more about this little patch of sky than almost any other. We know the positions of nearly 800,000 galaxies. We know their distances. We know their masses. We know their star formation rates. We know the temperature and density of the gas surrounding them. And now, we know the dark matter that holds them all together. The cosmos field is the Rosetta Stone of the cosmos. And the 2026 Dark Matter Map is the newest translation. Let us return now to the technology, to the actual process of making the map, because it is worth appreciating just how hard this was. Weak gravitational lensing is one of the most challenging measurements in all of observational science. Here is the problem. You need to measure the shape of a galaxy with incredible precision. A galaxy might be 10 billion light years away. It might be only a few pixels across in your image. And you need to determine whether that galaxy is slightly elongated, by maybe 1%, in a specific direction. That is the signal. That tiny distortion is the fingerprint of dark matter. But everything conspires to make this hard. The telescope itself has a point spread function, a way that it smears out the light from a point source. This smearing can mimic lensing. You need to model it and remove it. The detector has noise. Cosmic rays hit the camera and create false signals. The atmosphere, if you are on the ground, blurs the images. And the galaxies themselves are not perfect circles. They come in all shapes: spirals, ellipticals, irregulars, bars, rings. You need to statistically separate the natural shapes from the lensing-induced distortion. And you need to do it for hundreds of thousands of galaxies. This is why the Cosmos Webb team spent years developing their analysis pipeline. They calibrated the telescope's point spread function using thousands of stars. They modeled the noise properties of the detector. They developed algorithms to measure galaxy shapes with precision better than 1%. They tested their methods on simulated data, where they knew the answer, before applying them to the real sky. Every step was checked and double-checked. Every potential source of error was identified and mitigated. The resulting map is not just a pretty picture. It is a precision instrument, a scientific measurement of extraordinary fidelity. And the numbers tell the story. The JWST map achieves a galaxy number density of about 129 per square arc-minute. Compare that to ground-based telescopes, which typically achieve less than 20 per square arc-minute, or Hubble, which reached about 71. More galaxies means more measurements, More measurements means less noise. Less noise means a sharper map. The angular resolution of the map is 1 arcminute. Previous space-based maps of comparable area had resolutions of about 2.5 arcminutes. The improvement is more than a factor of 2. That is the difference between seeing a forest and seeing the individual trees. This level of precision opens doors that were previously closed. It allows scientists to study the dark matter distribution around individual galaxy groups, not just massive clusters. It allows them to trace filaments with greater confidence. It allows them to measure the profiles of dark matter halos, the way density drops off from the center to the edge, and compare those profiles to the predictions of different dark matter models. Each measurement is a test. Each test brings us closer to the truth. Let us also appreciate what the map looks like in terms of scale. The Cosmos Webb field covers 0.54 square degrees. That sounds small, and on the sky it is. But think about what is inside that tiny window. Nearly 800,000 galaxies. Some of them are nearby in cosmic terms, a few billion light years away. Others are incredibly distant. The team traced dark matter out to a redshift of about 2, which corresponds to a look-back time of roughly 10 billion years. They are seeing galaxies as they were when the universe was less than a quarter of its current age. That means the map is not just a spatial snapshot. It is a temporal window, a view through time. The galaxies in the foreground show the dark matter web as it looks now. The galaxies in the background show the web as it looked billions of years ago. By combining these layers, the scientists can create a time-resolved picture of the cosmic web's evolution. They can see how the filaments grew thicker, how the nodes became more massive, how the voids expanded, all encoded in the subtle warping of galaxy shapes. There is something deeply moving about this. We built a machine, a telescope, a camera, a set of mirrors and sensors and computers. We launched it 1 million miles from Earth. We pointed it at an empty patch of sky. And from the barely perceptible warping of light from nearly 1 million galaxies, we extracted the shape of something invisible. Something that outweighs everything visible in the cosmos by 5 to 1. Something that built the universe. And we drew its picture. If that is not one of the greatest achievements of our species, I do not know what is. Now let us think about what comes next. Beyond the current maps, beyond the current telescopes, what is the ultimate goal of dark matter science? Where are we heading? The dream is threefold. First, map the dark matter web in 3 dimensions across the entire observable universe. Not just a patch, not just a slice, all of it. A complete 3-dimensional atlas of the invisible. This is a generational project. It will take decades and multiple telescopes, but it is the goal. Euclid, Roman, Rubin, and future telescopes not yet named will contribute. Each one adds another layer. Each layer sharpens the picture. Second, identify the dark matter particle. Despite decades of searching, we have not caught it yet. The LZ experiment has pushed the limits to extraordinary levels. The ADMX experiment is searching for axions. New ideas like looking for dark matter in gravitational waves are being explored, and the maps themselves may eventually help. If we can determine the exact properties of the dark matter web, the precise shape of its halos, the exact behavior of its smallest structures, we can narrow the list of candidates to just one. The map may tell us what dark matter is, not by detecting a particle, but by describing its behavior so precisely that only one type of particle could produce it. Third, understand how dark matter and dark energy work together to shape the universe's fate. Dark matter pulls things together. dark energy pushes things apart. The battle between them determines the future of the cosmos. Will the universe expand forever, diluting the web into thinner and thinner strands? Will the expansion slow and reverse, collapsing everything back into a single point? Or will the universe settle into a state of gentle, eternal expansion, with the web frozen in place, galaxies slowly fading to darkness? The answer depends on the properties of dark matter and dark energy. And the maps, by tracking how the web changes over time, are the key to determining which future awaits us. There is a thought experiment that cosmologists sometimes use to illustrate the importance of dark matter. Imagine removing it. Imagine a universe identical to ours in every way, except that the dark matter is gone. What would happen? The answer is, everything would fall apart. Not slowly, not gradually, catastrophically. Without dark matter, the cosmic microwave background would look different. The tiny density fluctuations would not have had enough gravitational pull to grow into structures. The first dark matter halos would never form. And without those halos, ordinary matter would have nothing to fall into. No gravitational valleys, no cosmic cradles. Gas would drift aimlessly through the expanding universe, never gathering enough mass to form a star. No stars means no nuclear fusion. No nuclear fusion means no heavy elements. No heavy elements means no rocky planets. No rocky planets means no water. No water means no life. The entire chain of events, from the Big Bang to you sitting here right now, depends on dark matter. Remove it, and the universe is nothing but a thin, cooling, expanding fog of hydrogen and helium. Forever. No structure, no complexity, no light, no life. Just an eternal drift into darkness. That is the weight of what the 2026 map reveals. Not just a scientific measurement, a statement about the preconditions for existence. The invisible web is not a curiosity. It is a necessity. Without it, there is nothing. Let us think about the names, the people behind this discovery. Because science is not done by telescopes alone. It is done by people. People who dedicate their careers, their sleepless nights, their creative energy to understanding the universe. Diana Scognamiglio, who led the study, a postdoctoral researcher at JPL. She started her postdoc in early 2023, just as the first Cosmos Web data was arriving. She watched the raw images come in from JWST and knew she was looking at something special. She spent years developing the techniques to turn those images into a map of the invisible. She presented the preliminary results in May 2025 to an audience of colleagues who erupted in applause. Gavin Leroy, a researcher at Durham University, who co-led the study. He brought expertise in mass map reconstruction, the mathematical art of turning galaxy-shaped measurements into a picture of the underlying mass distribution. David Harvey, who contributed to the analysis of lensing systematics, the subtle errors and biases that can creep into weak lensing measurements if you are not careful. Richard Massey, also at Durham, a veteran of dark matter mapping, who helped create the original Hubble Cosmos dark matter map in 2007. He saw the field go from a blurry sketch to a sharp photograph. Jason Rhodes, at JPL, who has spent his career developing the tools for weak lensing analysis, and Bahram Mobasher, at UC Riverside, a founding member of the Cosmos Project, who helped build both the 2007 Hubble map and the 2026 JWST map. These are the cartographers of the dark, the map makers of the invisible. They did not discover dark matter. That credit belongs to earlier generations, to Zwicky and Rubin and their colleagues. But they did something equally important. They drew its portrait. They showed us what it looks like. They turned a concept into a picture. And in doing so, they changed our relationship with the universe, because seeing changes everything. Before the map, dark matter was an idea, a number in an equation, a placeholder in a cosmological model. It was real, yes. Scientifically established, yes. But it was abstract, intellectual, remote. The map made it concrete, tangible, visual. You can look at the map and point to a filament and say, there, right there. That is a river of dark matter. It stretches for millions of light years. And along its banks, galaxies are growing. You can point to a void and say, there is the emptiness, the gap, the place where dark matter is thin and galaxies are scarce, the negative space of the cosmos. Seeing the invisible changes how you think about the visible. Once you know the scaffolding is there, you can never look at a galaxy the same way again. You know it is not floating freely. It is perched on a dark matter thread, held in place by invisible gravity, connected through the web to every other galaxy in the universe. The cosmos is not a collection of isolated islands. It is a network, a web, a living, growing, evolving structure held together by something we cannot see, but can now, for the first time, map. And that brings us to the final thought, the one that lingers after the data is analyzed and the papers are published and the telescopes move on to their next targets. It is the thought that strikes you when you look up at the night sky on a clear, dark night, knowing what you now know about the invisible web that holds it all together. You are part of this web, not in a mystical sense, in a physical sense. The atoms in your body were forged in stars that were born in galaxies, that were shaped by dark matter halos that formed along filaments of the cosmic web. The gravitational influence of dark matter reached across billions of light years and billions of years to create the conditions that eventually, through an unimaginably long chain of cause and effect, produced you. You are standing on a planet that orbits a star that sits in a galaxy that is embedded in the web. The web is not out there, somewhere far away. It is here. It is everywhere. It is the fabric of reality itself. And when the James Webb Space Telescope stared at that quiet patch of sky in the constellation Sextans, and when it measured the shapes of 800,000 galaxies, and when Diana Scognamiglio and her team turned those measurements into a map of the invisible, what they were really doing was showing us the bones of the universe, the skeleton beneath the skin, the framework beneath the facade, the architecture beneath the artwork. We live in a universe that is mostly invisible. 95% of it is beyond our senses. Dark matter, dark energy, hidden, silent, unseen, and yet it is the invisible 95% that built everything, that shaped everything, that holds everything together. The visible 5%, the stars and planets and galaxies and people, is the thin, bright layer on top of a vast, dark foundation. And now we have a map, the first real map, the first detailed portrait of the invisible foundation. And it is beautiful, not in the way a sunset is beautiful, not in the way a flower is beautiful. It is beautiful in the way truth is beautiful, in the way understanding is beautiful, in the way knowing is beautiful. It is the beauty of discovery, the beauty of seeing something for the very first time, something that was always there but never visible, something that built you and me and everything we have ever known. The invisible atlas is open. The first page has been drawn. And as you drift off tonight, imagine it, the web, stretching across the darkness, connecting everything, holding everything, silent, invisible, eternal, the scaffolding of the cosmos, the backbone of reality, the dark architecture of everything that is, and somewhere, 1,000,000 miles from Earth, A golden mirror is still floating in the cold, still collecting light, still measuring the shapes of distant galaxies, still adding lines to the map. The atlas is not finished. It has barely begun, and the next page is waiting to be drawn. If you enjoy this kind of journey through the cosmos, please consider subscribing to the channel. It helps us make more of these deep explorations into the greatest mysteries of science. And if you want to keep learning, check out some of our other videos on the universe's biggest questions. Leave a comment below and tell us what you want to explore next. Until then, sleep well, dream deep, and remember, you are part of the web. But before you close your eyes, let us sit together a little longer. Because there are still corners of this atlas worth exploring. There are still depths to plumb. There are still questions to ask. And the night is long. Let us think about gravity, the one force that dark matter obeys, the one thread that connects the invisible to the visible. Gravity is the oldest force we know. It is the first one humans noticed. An apple falls from a tree. A stone rolls downhill. The moon circles the earth. The earth circles the sun. Newton described it in the 1600s. Einstein reimagined it in 1915. And yet, for all we know about gravity, it remains the most mysterious of the fundamental forces. It is the weakest force by far. Pick up a paperclip with a small magnet, and you have just demonstrated that the electromagnetic force of a tiny magnet can overpower the gravitational pull of the entire Earth. And yet, gravity shapes everything on the largest scales. It forms planets. It ignites stars. It builds galaxies. It weaves the cosmic web. How can the weakest force be the most powerful architect? The answer is range. Gravity reaches everywhere. It never turns off. It never cancels out. Electromagnetism has positive and negative charges that can balance each other. But gravity has only one polarity. It only attracts. It adds up. A galaxy's worth of matter pulls together. A cluster's worth of matter pulls even harder. And dark matter, being so abundant, contributes the lion's share of that gravitational pull. This is why dark matter matters so much. Pun, very much intended. It is the dominant source of gravity in the universe. And gravity is the dominant force that shapes the universe. So dark matter, through gravity, is the dominant architect. The visible matter, the stuff we are made of, is along for the ride, riding the gravitational waves created by something we cannot see. Now let us think about something specific that the 2026 map revealed. Something about the relationship between dark matter and the galaxies sitting inside it. Scientists call this the stellar mass to halo mass relation. It describes how the mass of stars inside a galaxy relates to the mass of the dark matter halo that surrounds it. And it is not a simple relationship. You might expect that bigger dark matter halos produce bigger galaxies. More dark matter means more gravity. More gravity means more gas falls in. More gas means more stars. Simple. But it is not that simple. The relationship is more like a bell curve. At the low end, small dark matter halos host small galaxies, but the galaxies are much less massive than you would expect from the halo size. Something is preventing the gas from forming stars efficiently. At the high end, the same thing happens. The most massive dark matter halos, the ones that host galaxy clusters, also have less stellar mass than you would predict. Something is shutting down star formation in those environments. The sweet spot is in the middle. Halos with a mass of about 1 trillion times the Sun, roughly the mass of the Milky Way's halo, are the most efficient at turning gas into stars. They hit the Goldilocks zone. Not too small, not too big, just right. What causes this pattern? In small halos, the culprit is probably supernovae. Young, massive stars explode and blow gas out of the galaxy, preventing it from forming more stars. The gravitational well of a small halo is not deep enough to hold onto the gas after a supernova goes off. The gas escapes into space. Star formation sputters and stalls. In large halos, the culprit is probably something different. Active galactic nuclei. Supermassive black holes at the centers of massive galaxies that blast jets of energy outward, heating the surrounding gas and preventing it from cooling and collapsing into stars. This process, called feedback, keeps the most massive galaxies from growing as large as they could. The black hole acts as a thermostat, regulating the temperature of the gas and keeping star formation in check. The Cosmos Webb map, by revealing the dark matter halos around galaxies of different sizes, provides new data to study this relationship. Scientists can measure the halo mass from the weak lensing signal and the stellar mass from the galaxy's light. They can plot one against the other and see how efficiently different halos convert gas into stars. And they can do this not just for the nearby universe, but for galaxies billions of light years away, where the universe was younger and the relationship might have been different. Understanding this relationship is crucial because it tells us how galaxies form and evolve. It tells us why the Milky Way looks the way it does, why some galaxies are giant and red and dead, why others are small and blue and furiously forming stars. The answer, in every case, starts with the dark matter halo. The halo sets the stage. It determines the size of the gravitational well, the amount of gas that falls in, the efficiency of star formation, and the ultimate fate of the galaxy. Everything starts with the dark matter. Everything flows from the invisible. Let us continue our walk through the implications. Because the dark matter map does not just affect astrophysics. It touches particle physics. It touches fundamental physics. It touches our deepest understanding of reality. Consider this: the standard model of particle physics, the theory that describes all known fundamental particles and 3 of the 4 fundamental forces, has been tested to incredible precision. It predicted the Higgs boson years before it was discovered. It predicted the existence of the W and Z bosons. It predicted the behavior of quarks and leptons with extraordinary accuracy. It is one of the most successful scientific theories ever constructed. But it has a problem, a big one. It does not include dark matter. Not a single particle in the standard model can account for the dark matter we observe. Neutrinos come closest. They are neutral. They barely interact with anything, but they are too light and too fast. They would produce a cosmic web that is too smooth, too diffuse. They cannot be the dark matter. Whatever dark matter is, it is something new. Something that the standard model has no room for. Something that demands new physics. This is why the 2026 map is so exciting for particle physicists. Because the map does not just tell us where dark matter is, it constrains what dark matter can be. The shape of the halos, the width of the filaments, the number of small structures, all of these features depend on the properties of the dark matter particle. Its mass, its self-interaction cross-section, its temperature, its quantum properties. By measuring the web, we are indirectly measuring the particle. For example, if dark matter is made of very light particles, sometimes called fuzzy dark matter, with masses around 10 to the negative 22 electron volts, something extraordinary happens on small scales. The quantum nature of these ultralight particles creates a wave-like behavior. The smallest dark matter halos would not be sharp and cuspy. They would be smooth and spread out, with solitonic cores. the filaments of the cosmic web would be slightly thicker, with periodic density variations like standing waves on a string. The web would have a minimum grain size below, which structures cannot form. And if we could detect these features in the map, it would be strong evidence for fuzzy dark matter. On the other hand, if dark matter is a conventional cold particle, a WIMP-like object with a mass of perhaps 100 times the proton mass, the web looks different. The halos are cuspy. The filaments are thin and sharp. Small structures abound. The web has no minimum grain size. It is fractal-like, with structures on every scale down to the resolution limit of our observations. The current JWST map does not yet have the resolution to definitively distinguish between these scenarios, but it is getting closer, and the next generation of maps combining JWST, Euclid, Roman, and Rubin data will push further. Each improvement in resolution is a tightened constraint on the dark matter particle. Each new feature detected is a test of the theory. The web is the experiment. The galaxies are the data. The dark matter particle is the unknown variable. Let us think about one more thing, one more aspect of the 2026 discovery that deserves attention. And it is something that is easy to overlook in all the excitement about dark matter halos and cosmic filaments. It is the role of time. The universe is 13.8 billion years old. The light from the most distant galaxies in the Cosmos Webb survey has been traveling for over 10 billion years. That means when we look at those galaxies, we are seeing the universe as it was 10 billion years ago. We are seeing the cosmic web in its youth. We are seeing the dark matter scaffolding before it was fully built. And this is profound, because it means the map is not just a spatial document. It is a temporal one. It is a history, a record of how the invisible universe has changed over the vast sweep of cosmic time. In the distant layers of the map, the filaments are thinner, the clusters are smaller, the voids are less defined. Everything is younger, smaller, simpler. In the nearby layers, the web is mature, thick filaments, massive clusters, vast empty voids. The contrast between then and now is a record of the growth of structure, a chronicle of how gravity, dark matter, and time conspired to build everything. This temporal depth is one of the most powerful features of weak lensing surveys. You get the map for free, in a sense, because the galaxies you are measuring are at different distances. They automatically sample different cosmic epochs. You do not need to run a time machine. The time machine is built into the universe itself. Light speed is finite, distance is time, and every galaxy in the survey is a clock, telling you what the universe looked like when its light began its journey. The team plans to exploit this temporal depth in future work. By slicing the data into redshift bins, thin slabs of cosmic time, they can create a sequence of maps that show the web at different ages, a cosmic flipbook. Watch the filaments grow. Watch the clusters assemble. Watch the voids expand. Watch the invisible architecture of the universe emerge from the primordial fog, one cosmic epoch at a time. This is not speculation. This is the plan. The data already exists. The analysis is underway. And the results, when they come, will provide some of the most stringent tests of lambda CDM that we have ever performed. Let us return one more time to the feeling, the texture, the experience of this discovery, because this is a cosmic drift journey, and the destination is not just the data. The destination is the wonder. Picture yourself lying on your back in an open field. It is nighttime. The sky is clear. No moon. No city lights. Just stars. Thousands of them. The Milky Way arches overhead like a luminous river. You feel small. You feel the weight of the sky, the depth of it, the vastness of it. Now imagine that you could see the dark matter. Imagine that someone gave you special glasses that reveal the invisible. You put them on, and the sky transforms. The scattered stars are still there, but now you see the threads. Thin, ghostly blue threads stretching between the galaxies, weaving between the clusters, forming a vast net that covers the entire sky. Every star, every galaxy, every bright point of light sits at a node or along a filament or near the edge of a void. Nothing is alone. Everything is connected. The web is everywhere. You take off the glasses. The threads disappear. The sky looks normal again. Stars and darkness. But you know the truth now. You know the web is there. You know it has always been there. And you know that without it, the stars would not exist. The sky would be empty. The universe would be dark. Not just dark as in lacking visible matter. Dark as in empty. Dark as in void. Dark as in nothing. That is the gift of the 2026 map. Not just knowledge, understanding. Not just data, insight. The invisible universe has been made visible, and it is more beautiful than anyone could have imagined. Not beautiful in the way we usually think of beauty. Not colourful or symmetrical or elegant. Beautiful in the way a skeleton is beautiful. In the way a blueprint is beautiful. In the way a root system is beautiful. The hidden infrastructure that makes the visible world possible. The philosopher Heraclitus said, over 2,000 years ago, that nature loves to hide. He was right. The universe's deepest truths are not written on its surface. They are buried beneath it, hidden in the spaces between the stars, embedded in the warping of light, encoded in the shapes of galaxies a billion light years away. And it takes extraordinary patience, extraordinary cleverness, extraordinary technology, and extraordinary teamwork to pull those truths into the light. The Cosmos Webb team pulled one of the greatest truths into the light, the truth that the universe has a skeleton, an invisible frame, a dark architecture. And that architecture is not random. It is not chaotic. It is structured, organized, patterned, beautiful. It is a web, a cosmic web, woven by gravity and dark matter over 13.8 billion years. And it contains everything, every galaxy, every star, every planet, every living thing, you. The Atlas of the Invisible has its first detailed page. The constellation Sextans, the sextant, the navigator's tool, has guided us to our position. And our position is this: we are tiny. Time, il a ones. We are brief. We are made of the 5%, but we are part of the web, connected to every filament, shaped by every halo, descended from every primordial density fluctuation that dark matter amplified into a galaxy. And the map is open, spread out before us. Blue contours on a dark background, the bones of the universe, the scaffolding of reality, the invisible architecture of everything. Let us take one more detour before we say goodnight. Let us think about the voids, because we have spent most of this journey talking about where dark matter is, the filaments, the clusters, the halos, the dense regions. But the voids, the places where dark matter is not, are equally important and equally fascinating. Cosmic voids are the largest structures in the universe, and that sounds like a contradiction. How can empty space be a structure? But voids are not just the absence of matter. They are shaped regions, defined regions, bounded regions. They are the bubbles in the cosmic sponge, the air pockets in the bread, the spaces between the strands of the web. And they are enormous. Some voids are over 300 million light-years across. A single void can be larger than many superclusters of galaxies. If you were somehow placed in the center of a cosmic void, you would see almost nothing in any direction. A few dim, distant galaxies far, far away, but mostly just emptiness, darkness, silence, the quietest neighborhood in the universe. And yet, voids are not completely empty. They contain a thin mist of dark matter, a faint, diffuse background. Measurements suggest that the density inside a void is perhaps 10 to 20% of the cosmic average. That is thin, very thin, but it is not zero. The void still has mass. The void still has gravity, just not enough to hold on to galaxies or build structures. Matter flows out of the voids, streaming toward the filaments and clusters, leaving the voids increasingly empty over time. In the 2026 Cosmos Webb map, the voids appear as pale, low-density regions between the bright filaments and clusters. They are clearly visible, and their shapes and sizes provide important cosmological information. The size distribution of voids, how many big ones versus small ones, depends on the cosmological model. It depends on the total amount of dark matter, the nature of dark energy, and the growth rate of cosmic structure. By measuring the void sizes in the map and comparing them to theoretical predictions, scientists can test lambda CDM from a completely different angle. Voids are the other side of the coin, the negative image. And sometimes, the negative image reveals details that the positive image hides. There is something poetic about the voids. They remind us that the universe is mostly empty. Most of the volume of the cosmos is void. The filaments and clusters and galaxies occupy a small fraction of the total space. We live in the dense part, the busy part, the part where things happen. But most of the universe is quiet, still, almost nothing. And that nothingness has a shape. It is carved by gravity, sculpted by dark matter, defined by the same forces that built the web. The emptiness is not random. It is structured. It is meaningful. It is part of the architecture. Imagine walking through a cathedral. You admire the columns, the arches, the stained glass, the altar. These are the structures, the built things. But the experience of the cathedral depends equally on the space between those structures. The height of the ceiling, the width of the nave, the openness of the transept. The emptiness is designed. It is intentional. It is part of what makes the cathedral what it is. The cosmic web is the same. The voids are not just the gaps between the structures. They are part of the design, part of the architecture, part of the beauty. Now let us think about something else that the 2026 map points toward, and it is something that might surprise you. The connection between dark matter and life. We have already talked about this in broad strokes. Dark matter built the scaffolding. Galaxies formed along the scaffolding. Stars formed in the galaxies. Stars made the heavy elements. The heavy elements made planets. Planets, under the right conditions, gave rise to life. The chain of cause and effect runs from the cosmic web straight to biology. But let us be more specific. Let us trace the chain in more detail. About 10 billion years ago, in a region of the cosmic web that would eventually become our corner of the Milky Way, dark matter was gathering. A halo was forming. It was not one of the biggest halos, not a cluster-scale behemoth, just a modestly large halo, maybe 1 trillion times the mass of the Sun, enough to hold on to a significant amount of gas, enough to create a gravitational well deep enough for that gas to cool and collapse. And it did. The gas fell into the dark matter halo. It cooled, it spun, it flattened into a disk, and within that disk, it began to fragment. Dense knots of gas collapsed under their own gravity, heating up, compressing, until the pressure and temperature at the center reached the threshold for nuclear fusion. Hydrogen atoms smashed together and became helium, and the first stars of the proto-Milky Way ignited. Those early stars burned through their fuel and exploded. Each explosion scattered a fresh batch of heavy elements into the gas. Carbon from the triple alpha process, oxygen from helium burning, iron from the collapse of the stellar core, elements that had never existed before the stars forged them. And those elements mixed back into the gas, enriching it. The next generation of stars that formed from that enriched gas had more heavy elements, and the generation after that had even more. Over billions of years, this cycle continued. Stars born, stars died, elements scattered, gas recycled. The chemical composition of the galaxy slowly changed. And eventually, about 4.6 billion years ago, in an unremarkable arm of the Milky Way, a cloud of gas and dust, rich with the accumulated elements from billions of years of stellar recycling, began to collapse. It formed a star, our Sun, and around it, a disk of leftover material. And in that disk, the heavy elements, the carbon, the oxygen, the silicon, the iron, the stuff that dark matter's gravity had allowed the universe to create. Those elements condensed into grains. Grains stuck together, grew into pebbles. Pebbles grew into boulders. Boulders grew into planetesimals. And planetesimals grew into planets. One of those planets, the third from the Sun, settled into an orbit that was not too hot and not too cold. It had water. It had an atmosphere. It had a magnetic field to protect it from the solar wind. And within a few 100 million years, something extraordinary happened on its surface. Chemistry became biology. Molecules began to replicate. Life began. All of this, every step, traces back to the dark matter web. Without the halo, no galaxy. Without the galaxy, no stars. Without the stars, no heavy elements. Without the heavy elements, no planet. Without the planet, no life. Without the web, no you. The connection is not metaphorical. It is causal. It is physical. It is real. And the 2026 map shows us this connection more vividly than ever. When you look at the map and see a dark matter filament, you are looking at the kind of structure that built our galaxy. When you see a dense knot in the map, you are looking at the kind of environment that nurtured the first stars. When you see the galaxies strung along the web like jewels on a necklace, you are looking at the same process that eventually created Earth. The map is not just a picture of the distant cosmos. It is a family portrait. It shows us where we come from. Let us think about one more thing, the future of the web itself. Because the cosmic web is not finished. It is still evolving, still growing, still changing. Filaments are still thickening. Clusters are still merging. Voids are still expanding. The universe is still in motion. And the future of the web depends on the interplay between two opposing forces. Dark matter, which pulls things together, and dark energy, which pushes things apart. Right now, dark energy is winning. The expansion of the universe is accelerating. The voids are growing faster. The distances between clusters are increasing. The web is being stretched, slowly, imperceptibly, but relentlessly. And if dark energy continues to dominate, as most models predict, the future of the web is one of slow dissolution. Not a dramatic collapse, not a sudden end, just a gradual thinning. The filaments will stretch, the voids will expand. Galaxies at the edges of the web will drift beyond each other's reach. The web will become thinner and thinner, more and more diffuse, until eventually, in the far, far future, billions and billions of years from now, each galaxy will be alone, isolated in an expanding void, unable to see or interact with any other galaxy. The cosmic web will have dissolved into the cosmic dark, But that is an unimaginably long time from now. For the moment, the web is here. It is strong. It is beautiful. And it is doing what it has always done. Holding everything together, building everything, connecting everything. The silent architect is still at work. And we, the brief, bright sparks of consciousness on a small planet in an unremarkable galaxy, in a modest corner of the web, have finally looked up and seen the architect's work. Not with our eyes, not directly, but through the subtle bending of light from nearly 1 million galaxies, through the patient work of scientists and engineers and mathematicians, through the lens of a golden telescope floating in the cold silence of space. The invisible universe has been mapped. The first page of the atlas has been drawn, and it shows us that we are not alone in the dark. We are part of the dark, woven into it, built from it, held by it. There is a concept in physics called emergence. It describes how complex structures arise from simple rules, how the rules of gravity, acting on simple particles over vast spans of time, produce the intricate cosmic web, how the rules of chemistry, acting on the heavy elements forged in stars, produce the staggering complexity of biology, how simple beginnings lead to complex endings, how the universe builds itself from the bottom up. The dark matter map is a picture of emergence. It shows us the simple becoming complex, the smooth becoming structured, the invisible becoming visible, the nothing becoming everything. The cosmic web is the universe's masterwork of emergence, built from nothing but gravity and particles and time. And from its threads, everything we know has emerged. That is the story the map tells. Not just a scientific story, a cosmic story, a human story. The story of how the invisible built the visible, how the dark made the light, how the quiet, patient pull of gravity, acting on a substance we have never touched, wove a web that eventually produced creatures capable of wondering about it. Sleep well tonight. Sleep knowing that the web holds you, that the scaffolding is strong, that the invisible architect has been building for nearly 14 billion years, and that somewhere right now a golden telescope is floating in the cold darkness, adding another line to the map, drawing another thread of the web, revealing another corner of the invisible. The atlas grows, the picture sharpens, and the universe, in all its hidden glory, slowly comes into view. Let us sit with one final thought, a thought about perspective, about what it means to know what we now know. For most of human history, we lived in a universe that was small. The Earth was the center. The sun revolved around us. The stars were points of light on a celestial sphere, close and decorative. The universe was cozy, understandable, human-scaled. Then came Copernicus, and the Earth moved. Then came Galileo, and the moons of Jupiter revealed that the cosmos did not revolve around us. Then came Hubble, and the galaxies appeared, millions and billions of them, stretching across distances that stagger the mind. Each revolution in understanding made the universe bigger. And each time, humanity got smaller. The discovery of dark matter is perhaps the most humbling revolution of all, because it did not just make the universe bigger, it made it mostly invisible. It told us that everything we can see, every galaxy, every star, every planet, every person, is just the thin, bright surface of a vast, dark ocean. We are the foam on the wave, the frost on the window, the glow at the edge of something immense and unseen. And the 2026 map shows us the shape of that ocean for the first time. It shows us the currents and depths and contours of the invisible sea we are floating on. And it tells us that the sea is not chaotic, it is structured, organized, beautiful. a web of connections stretching across the entire cosmos, linking everything to everything else through the patient pull of gravity. There is a paradox here, a gentle one. The more we learn about the universe, the more mysterious it becomes. Each answer opens 10 new questions. Each map reveals 10 new territories to explore. We mapped the cosmic microwave background and discovered that the universe is flat. We mapped the galaxy distribution and discovered the cosmic web. We mapped dark matter and discovered that it is the dominant architect of all structure. And now we ask, what is the architect made of? What are its tools? What are its plans? We do not know, not yet. But we are looking. We are mapping. We are measuring. We are asking the right questions. And the 2026 Dark Matter Map, the first detailed page of the Invisible Atlas, is the most powerful tool we have ever had for finding the answers. There are experiments running right now, at this very moment, that might find the dark matter particle. Deep underground, in abandoned mines in South Dakota, and laboratories beneath the mountains of Italy, tanks of liquid xenon sit in the dark, waiting for a single dark matter particle to nudge a single xenon atom. The signal would be extraordinarily faint, a tiny flash of light, a minuscule transfer of energy, but the detectors are sensitive enough to see it. And every day that passes without a detection narrows the possibilities, tells us what dark matter is not, brings us closer, by elimination, to what it is. There are axion experiments too, in laboratories in Seattle and Europe. Resonant microwave cavities are tuned to specific frequencies, listening for the faint signal of an axion converting into a photon in the presence of a strong magnetic field. Axions are a theoretical particle, predicted by a solution to a problem in quantum chromodynamics. They are incredibly light. They interact incredibly weakly. But if they exist, they could be the dark matter. And the experiments are scanning through the frequency range, one small step at a time, looking for the telltale hum. And then there is the collider, the Large Hadron Collider at CERN, the most powerful particle accelerator on Earth. Protons smash together at nearly the speed of light, producing showers of particles. Most of those particles are familiar: quarks, gluons, electrons. But occasionally, if the energy is right, something new might appear. Something that escapes the detector without leaving a trace. Something invisible. If physicists see events where energy goes missing, where the total momentum does not add up, that could be the signature of a dark matter particle being created and slipping away into the dark. None of these experiments has found dark matter yet, but they are getting closer. The constraints are tightening. The net is closing. And the 2026 Dark Matter Map is helping to guide the search. It tells the particle physicists what the web looks like, what the halos look like, how dark matter behaves on different scales. And those observations constrain the particle's properties, its mass, its interaction strength, its quantum nature. The map and the detectors are two halves of the same search. The astronomers looking down from the sky, the physicists looking up from underground. And somewhere in between, in the gap between the map and the detector, the answer is waiting. The story of dark matter is the story of humanity reaching beyond its senses, beyond what can be seen or touched or heard, into the invisible, into the unknown, into the dark. And the 2026 map is the most vivid expression of that reach that we have ever produced. It is a portrait of the unseen, a picture of the hidden, a map of the invisible architecture that holds everything together. And it is just the beginning. The atlas grows, the picture sharpens, and the universe, in all its hidden glory, slowly comes into view.